Welcome to the 17th lecture of graph theory. So, in the last class we were discussing about planar graphs. So, the main thing that we proved in the last class was that for any connected planar graph, so the number of edges is 3n minus 6. The number of edges were at most 3n minus 6. Now, using this bound for the number of edges, we can show that the planar graphs can be 6 colored. This is what we will go next. Any planar graph can be vertex colored using 6 colors. So, how do we do this thing? So, the first thing, we need two observations. One is if you take any planar graph and any of its subgraphs, induced subgraph or subgraph, it will again be planar graph. Why is it so? Because if this graph can be drawn on the plane without the edges crossing each other, then definitely any subgraph of it also can be drawn. We just have to delete the vertices or edges which are not part of our selection, right. So, therefore, that is one point. The second thing is that because the number of edges is at most 3n minus 6 and 6, sum of degrees, if you add up the degrees of the vertices, is at most how much? 6n minus 12. That is because each edge contributes 2 each to the sum. So, if there are only 3n minus 6 edges, a maximum of 6n minus 12 can come from such a sum. And now, if that is the situation, we know that there exists a vertex, say x of degree at most 5. Why is it so? Because if this is the sum of degrees and if all degrees were 6 or more, then the total will be at least 6n, right, 6n, which is greater than 6n minus 12. So, there should be at least one vertex whose degree is at most 5. This is the main thing. So, in that case, what we can do is an inductive coloring, namely, or in other words, what we can do is to arrange the vertices in an order. Say we can arrange the vertices in an order this way. Say let us say x1, x2, x3. So, this xn be the vertices. So, x1 is the vertex of degree 5. So, if you look at the neighbors of x1, so there are only at most 5 neighbors to this side, right, among these things. Now, if you look at the graph on x2 to xn, that is again a planar graph. We will select x2 in such a way that is a vertex of degree at most 5. We know that any planar graph has a vertex of degree at most 5, and in particular this induced planar graph on x2, x3 up to xn also has one. And then without loss of generality, let us name that vertex with degree at most 5 to be x2. So, it means that the number of neighbors of x2 in this collection is at most. It may be possible that there can be connection backward, but that does not count. We just count these neighbors, the forward going neighbors. And then similarly, x3 is that vertex whose minimum degree is at most 5 in this induced graph of x3 to xn. So, there is at most 5 neighbors in this collection, at most 5 neighbors in this collection. So, the ordering is such that if you take xi, so its number of neighbors in xi plus 1, xi plus 2 up to xn is at most 5. And then we start coloring from xn onwards. We first color xn with an arbitrary color, this will be colored first, and then xn minus 1 will be selected. So, that will be given icon. So, when up to xi plus 1 to xn we have colored using at most 5 colors, at most 5 colors, right, sorry, at most 6 colors, right. Let us see. So, now I consider xi, we know that in this collection it has only 5 neighbors at most, and then therefore, how many colors are used up already? Only 5 colors are used up maximum, because this can take, these all can take different colors, a total of 5 colors may be used up. Now, this can use the 6th color available, right, 6th color available. So, like that we can go all the way up to x1, and then once x1 is also colored using at most 6 colors. So, the planar graph is 6 colored. The key idea here is not new, because we have already discussed this kind of coloring when we studied the greedy algorithm. There we were just saying that any vertex will have at most delta neighbors. So, therefore, delta plus 1 colors are enough, but here we have a special ordering in such a way that any vertex is only adjacent to at most 5 neighbors in the higher in the list of higher numbered vertices, right. So, that is why we can color it with 6 colors. So, this is the simplest color, the simplest procedure to color the planar graph, that is using 6 colors. Now, we will show how this can be improved. In fact, it is possible to show that any planar graph can be colored using at most 5 colors. How will you do that? So, again an inductive strategy, we will have to order the vertices in the in such a way that if I take xi, the number of vertices which are adjacent to it from the list xi plus 1 onwards to xn should be at most 5. The same listing will say we will inductively color. So, first xn will be colored, xn plus 1 will be colored, but this time we are making sure that we only use 5 colors. So, up to xi plus 1 we managed using 5 colors. Now, to deal with the xi with xi, the new we will see how it happens. So, xi as we have discussed, it has only 5 neighbors at most, right, it can be less. So, 5 neighbors at most. Now, by induction we know that we have already colored the vertices starting from xi plus 1 to xn. So, all these vertices can be assumed to have some color, right, we can assume that these are all colored already. Right. So, see if xi has less than 5 neighbors, then we will see only 4 or less colors. So, we can use the 5th color for xi. So, we will assume that there are 5 neighbors, and what if there is a repetition of colors on the set of neighbors, for instance the yellow is repeated twice, which means that only yellow, red, green and violet is used. So, only 4 colors are used, the 5th color will be available for xi. I can use the 5th color to color xi. So, we can assume that all the 5 available colors are present on the neighbors of xi, that means there is no repetition of colors. So, maybe I can select another color, black color say. So, this is so these are all black, yellow, violet, green and red. So, all are differently colored. Then how will I manage to get a color here without conflict, right. So, this is what we are going to discuss now. So, we can assume that, so this is this xi. So, around we can assume that we have, this is a common point xi, and then some distance we consider, it can be a very small distance, we can think that these are some epsilon distance this. So, therefore, we can assume that this is straight lines here. So, now so we can consider this black green vertices, right. So when you consider the black and green vertices, so we can consider, as we did earlier, we can consider the path so we can consider the path right, we can consider the path starting from black to green. So intuitively you can see that if you start from black to green, so it can either go like this and reach here, or it can either go like this and reach here. In whichever case, this path, right, if you trace out that path, any path, you can trace out any path. So the path will have to separate this red vertex from this or this, right, isn't it? So that is the key point. So it has to separate. So it can be like this. So you can see that this will complete a closed region, and then this will be inside and this will be outside. Or it can be like, yeah, right, for instance, you can think that the path can be the other way. So how can it be? So it can be, yeah, it can go like this and come here, but in that case also the red will come inside this closed region and this will be outside. So somehow this will separate this region containing red vertex from the yellow or violet vertex, right. Now the question is, can I have a path starting from okay, fine. So this is true about any path. Now the point is to consider a black green, the only black green vertices in the graph, black and green vertices in the graph, and so you see several connected components of black and green vertices will come if you consider only the black and green vertices. Now the question is, in which connected component this green vertex and this black vertex, that means this black vertex and this green vertex, the neighbors of this thing will appear. Is it possible that they belong to two different connected components, right? If suppose this black component belongs to a connected component, so black green we are saying, right. So it's possible, is it possible that it belongs to different connected components? Is it possible that it belongs to different connected components, right? No, it doesn't belong to different connected components. It's because if it belongs to different connected components, suppose this connected component of black and green is different from this, right, this is. So what we can do is, here we can exchange the colors green and black. So what we mean is, all the black vertices here will become green, that means these vertices will become green, and the green vertices will become black, that means these vertices will become black, right. So here in particular, yeah, this will become green, right. So then what happened is, there are two greens on the neighborhood. So there is a repetition of green color for this thing, as we discussed earlier. So the X is seeing green, yellow, violet and red only, no black. So black can be given to X, right. X can be colored with black color now. So this is what will happen. So what we can infer is that if you consider the green and black components formed by the green and black vertices. So the component in which the green neighbor is contained will be the same as the component in which this thing is contained. So in other words, it's that here there will be a connection between these two components, this and this. So somehow it will come all the way here and collect. So there will be some red green connection, red black connection all the way from here to here. So not red black, the green black color connection from all the way. So if there is a connected graph, then you can also see a red through the connected component containing this vertex and this vertex. We can also see a path. Right, we can also see a path of red and black vertices starting from this black neighbor of this x and reaching the green neighbor of x. So it will be like this. So if we have the new vertex and here we have its 5 neighbors. So we have selected the black vertex and we selected the green vertex, and let us say our path is like this: green, black, green, black, green, black, green, black, green, sorry, this is green, like this somehow. And as we have already discussed, that will separate this red vertex and say yellow vertex from each other. So now you can see that if you consider now the yellow and red islands, yellow and red connected components. So again we can argue that the yellow and red connected components should come in this. When you consider the yellow and red connected components, this vertex, this yellow neighbor and the red neighbor, they should belong to the same connected component, like as exactly as we argued for the black and green. So they should, because otherwise one of the connected component, in one of the connected components involving red and yellow vertices, we can exchange the colors yellow and red, and then that will cause a repetition of colors in the neighborhood of x, which means that one color is released, right. So it so happens that so we cannot do that, because if we have assumed that it cannot be colored, right. If we can color, then we are done. So it should happen that when you consider the red and yellow components, connected components, the same connected component should contain both these neighbors of yellow and red neighbors of our vertex, the central vertex, this new vertex. So it should so happen that, so there should be a red yellow path starting from this yellow neighbor to here, but how will it reach? It has to somehow cross this boundary we have drawn with green and black vertices. So it cannot cross it through any edge, right, because if it crosses through an edge, that means the edges are crossing, because it is a planar graph, we cannot do that. So this will come and this is not possible. So otherwise it is not a planar graph. So it should probably cross through one of the it should hit a vertex and get into this. But then hitting a vertex and getting into this will be a common vertex. This particular vertex will be common vertex for this green black path and the red yellow path. And which should be the color of this one, yellow or red or green or black? It is not possible, because if I say yellow, then this path will say no, this path allows only green and black. But if you say black or something, so then we will get a contradiction, because in the other part it should be a path, it should be a red or yellow vertex. So that is not possible. So it is not possible for it to come. So what we assume is, what we get now is that the same connected component cannot contain both this yellow neighbor and red neighbor, which means that there is this color switching strategy for one of them. So the one of the components can switch color, red to green, so it's red to yellow, so which essentially means that it will produce a repetition of colors there. and then that will allow us to color, use the other color, the fifth color for the central vertex. This is the idea. This is the idea of coloring. So, the next question will be, is it optimum? So, is it that is there a planar graph which requires 5 colors to vertex color it? The answer is no. In fact, planar graph can be colored using 4 colors. This was one of the most important questions in the history of graph theory. So, whether a planar graph, how do we color a planar graph with 4 colors, or is it possible to color every planar graph with 4 colors? We have already talked about the map coloring problem, so of Francis Guthrie. So, this so some several people attempted this, and then finally Appel and Haken came up with a proof using the help of computers. Finally, the proof is not so elegant in the sense that it requires computers for verifying finally some of the cases. So, then, but again this this is solved after almost a century of struggle. So, but the proof is so long that we cannot discuss the proof of Fourcolor theorem in this lecture. So, we will be happy with just the proof of 5 color theorem, right. Now, so we have already explained how planar graph can be 4 colored. So, our next intention is to go ahead with one more important theorem in planar, though it is not very related to the coloring. So, because we have started planar graphs, we will just get into this important theorem, a characterization of planar graphs, so by Kuratowsky. So, this is our next theme, and of course, so we will not give all the details because it will some of the details will take time. Therefore, we will just leave it, the simpler details we will leave it for the student to work out himself. So, but the main ideas we will cover. So, we have to, when I want to explain this result, I want to remind the student about some of the concepts we had earlier discussed. So, this is the one concept was that of minors. So, this was like when do we say that a graph is a minor of another graph. So, when do we say H is a minor of G? If you remember, it was when H can be got from G by repeatedly applying 3 of the following operations. One is delete a vertex, the second is delete an edge, the third is contract an edge. We are very familiar with these operations now. So, that is when we say that H is a minor of G. And second thing was that, yeah, correct. So, you will develop a, so we will say that suppose deletion of vertices and deletion of edges, let us forget. Suppose from G, if H can be obtained by a series of contractions, then we will say that G equal to M H. So, H is a minor of G, but from, so that means somehow G can be obtained from H by some reverse contractions. That is what we mean. So, though it is not very clear. So, what we intend to say is that you start from G, and if you apply a series of edge contractions, and if you can get H, then we will say that G equal to M H. This is the notation we want. And then similarly, so the another concept we had when related to minors was that of branch sets. For instance, if G equal to MH, then we can see G, the vertices of G as partitioned into a collection of vertices, a V1, V2, V3 up to all the way up to V say cardinality of H. That means, so the corresponding to each vertex of H I can get a collection of vertices of G, right. This is the branch set corresponding to the vertex set of H, right. And then, so we see that whenever, so this correspond to the vertices of the U1, U2, you can see, sorry, this is UH, right, U1, U2, U3. So the U1, U2, U3 may correspond to the vertices of H. Whenever there is an edge between Ui and Uj, we should get at least one edge between this collection, which is a vertex set of, it's a subset of vertex set of G, and between this collection, right. So that there should be at least, there can be more than one edges, but there should be one. So we should get a pattern like this. So this for instance, if you consider this as one vertex, and if you remove the multiple edges coming across this, then it should happen that we get back H. And moreover, there should be this should be a connected graph. For instance, if you look at the induced subgraph of G on the vertex set of V1 or V2 or V3 or anything, Vi in general, it should be an induced subgraph. This was the concept of branch set, right. And now let me remind you what was a topological minor, another one, topological minor. Topological minor means, so if so let us say suppose H is given. Now, so this is an H, this is a graph H, and now I can create a graph by subdividing this thing. Say H1 can be created by, say I decide to subdivide this H. That means so 1, 2, 3, right, this edge I have added here, I have added a vertex, and this is, so I can do it on another edge, I can keep on doing it, right. It is possible that I can do here, I can introduce a vertex here, a vertex here. So whatever graph we obtain by doing this thing, subdividing the edges, is called T of H, right, sorry, TH, we will call it TH after TH, we will call it TH. And if a graph G has a TH in it, contained in it, then we will say that the H is a topological minor of G. So it is contained in a subdivided form, that is what we say. We have discussed it before also, I just wanted to remind. So that the famous theorem of Kuratowsky says, if G is a planar graph, if G is planar, then we cannot find any TH in G where H is equal to K5 or K33, or in other words, we will not be able to find a TK5 or TK33 in G if G is planar. It is a obvious thing because K5 is a non-planar graph. We had already argued before, isn't it? We had argued in the last class that K5 is not a planar graph, and now if you take a non-planar graph and subdivide its edges, can it become non-planar graph? It is not possible. Suppose if I subdivide the edges and it becomes a planar graph, then why can't the original one also be planar? Because you can always contract it back. The same drawing will work with a little the in between vertices, introduced vertices should be deleted, and then we should use the same curve for the edge to denote it. So obviously, if we start with the non-planar graph and keep on subdividing its edges, it is not going to become non-planar. So planar, right. So as we had already seen, K5 is a is a non-planar graph, right. So, now the of course, so the it is with the one theorem we had proved in the last class, that a planar graph have at most 3n minus 6 edges. So, we can get a different proof for this K5 not being non-planar. So, because if you consider K5, it has how many edges? K choose 2, sorry, 5 choose 2 is equal to 10 edges, while 3n minus 6, if you substitute n equal to 5, will give us 9, because 5 into 3 minus 6 is 9 only. So, it says any planar graph with 5 vertices can only have 9 edges in it, but K5 has 10 edges, therefore, it cannot be planar. So, another way of proving it, right. K33 can we prove it? So, the same way. So, for instance, there are 6 edges, 6 vertices here. So, 6 into 5 is 20 minus 6 is 14, but we have only 9 edges here. That does not seems to work here, that same idea. So, sorry, so 3 and so 18 minus 6 is 12. So, which is a little more than the same idea is not working. So, but we can refine the idea of 3n minus 6, noting that K33 does not have any triangle, its smallest cycle is 4 cycle. It is up to the I can leave it to the student to work out the detail. So, K33, while so for instance, you can use the Euler formula, and then where we substituted for the number of edges, that so we had substituted that 3n by, so for each face is contributing 3 edges, we can say 4 edges, and then this will allow us to sharpen the inequality for this particular case, and then we can show that. So, that leave it to the student. So, here G is so Kuratowsky, coming back to Kuratowsky's theorem, we are saying this obvious 2 graphs K5 and K33. So, when I subdivide it, and if so definitely those cannot be planar. So, Kuratowsky says, so in a planar graph these cannot be there. Not only that, in any non-planar graphs we should get one of these things, either this subdivided K5 or a subdivision of K33, either TK5 or TK33. This is a very interesting statement, that is it is a characterization of planar graphs, right. So, to prove this thing, so we will in fact we will prove a little slightly different thing. We would rather prove that if see there is nothing, one side is very easy, as we have already seen, that is if it is a planar graph, then these topological minors will not be there, right. So, then if it is non-planar graph, this will be there, that is what we want to show, right. If it is non-planar, this will be there, or in other words, if these minors are not there, then it has to be planar graph. It has a plane drawing, on the plane without the edges crossing. This is what we want to show, right. So, in fact, what we will show is if a graph just does not have a K5 or K33 minor, then it is planar, is what we will show. So, it is equivalent, because we will explain why it is equivalent. We need not worry about topological minor, because if a graph has no K5 minor, then definitely cannot have a topological K5 minor also, because similarly if it has a K5 minor or K33 minor, then equivalently we can say that it should have corresponding topological minor. It is not true for every case, but in this particular case K5 K33 case, we can show that minor is enough, because topological minor is not very important, because we can say that if K5 minor is present, then K5 or K33 minor is present, definitely then K33 or K5 topological minor, one of the topological minor is also present, right. So, that is the interesting thing about it. And now let's remember some of the simple ideas, so which will help us to prove these things. One is this. So, suppose you have a graph x with maximum degree delta of x less than equal to 3, right. Suppose you have a graph x with maximum degree delta, for example x can be K33, right. This is why we are interested in such a statement. Then we say that if x is a minor of G, then x is also a topological minor of G. So, we will look at this statement. If delta of x is less than equal to 3, then every mx contains a Tx. Thus, every minor with maximum degree at most 3 is also its topological minor. This is what. How do we show that? Because see, what we are going to do is to consider a minor. So, mx, in fact the branch sets of that. So, you have this graph and then these are the branch sets, right. And see the degree if I consider one vertex, the degree is only 3. So, maximum degree is 3, at most 3. So, then you can take the minimum subgraph, in the sense that if some edge is not required in m of x, I will throw away that. So, which essentially means that within each of this branch set, the subgraph can be considered as just a tree, because you do not need more than a tree, spanning tree for connectivity. So, that just a tree is enough, and then just a tree is enough, and across each two of these things, if there is an edge in x, then we need only to keep one edge. So, there is no edge, then do not have to keep any. So, otherwise you just have to keep one edge, you do not have to keep more than one edge. This is by minimizing the number of edges used in mx. Given an x, I am getting an mx in such a way that it uses only the minimum number of edges in it for creating a minor x. So, now so the point now is to observe that if this, so inside this thing, so I can consider a tree. So, you can see like this. So, inside this thing I can consider a tree and including its neighbors in the other branch sets, because just there are 3 neighbors. So, it may so happen that so it may be like this, just 3 neighbors. So, now in this structure you can go back to, so see at some point these two has to meet, right. So, it may be meeting here somewhere, and then what about this will meet somewhere here, it need not be so it can be anywhere, but the third one wherever it meets. So, you see three paths going from here to here. So, essentially we can delete all other things, we just need these things, right. So, this can be a long path here. So, similarly in each of these things this structure will come. So, therefore, essentially there is no we can consider this vertex as a branch vertex, and then you can see that this is essentially a topological minor and not necessarily so complicated contractions are not necessary here. So, that is why we say that if x is a maximum degree 3 graph, the graph has only maximum degree 3, then if x is a minor of G, then x is indeed a topological minor of G also. You can also see in this way, right. So, that is one observation we wanted. The second observation what we want is suppose I will show that if we have a K5 minor or K33 minor for G, then G has also got a K5 topological minor or K33 topological minor. This is what we want to show. So, why is this true? Is it following from the earlier thing that no K33 for K33 minor, if there is a K33 minor by the earlier statement, because K33 is a maximum degree 3 graph. So, K33 minor implies K33 topological minor also. But K5 minor, suppose what if the graph has only K5 minor, it need not be K33 minor, right. So, if it has only K5 minor, the maximum degree here is 4 not 3. So, there is no guarantee that so we will get a K5 topological minor also. So, but what we are going to show is if there is a K5 minor, then either you get a K5 topological minor. If K5 topological minor is not there, then there will be a K33 minor, and in turn therefore a K33 topological minor. This is our plan. So, how will we do that? So, this is the idea. So, the idea is, so you just take the K5 minor, its branch sets are considered. So, the branch sets can be like this, 5 branch sets, by 5 branch sets are considered. Now, again the same idea of the taking the tree. So, we will so now you will minimize the this is an mx. So, and therefore, we will minimize the number of edges in the mx. So, for x is equal to K5 and then so therefore, this is here we get a tree like structure. So, tree only, and similarly here also there is a tree internally, because we do not need more than a tree for connectivity here, we can throw away all the remaining edges, and so everywhere. And then you see you can also assume that there is only one edge between any pair, because it is a K5, therefore, all pairs should have a connection between them like this. But we can of case get rid of the extra edges, we just need one edge for the getting a K5 minor. So, now what we do is, for each of these things we have a tree induced here, we have one here and one here and one here. So, this tree along with this 1 2 3 4 vertices can form a it will form a tree, right. So, it will look like this. So, some tree, and then we have, yeah, it can be some tree, and then it will go. So, this tree is extended. So, this is from one branch at this like this. So, now if you see that, so it is possible that you can go here, each of them go back, and then see they go back like this, and then this also go back like this and meet somewhere, and this also at the same point if all of these things meet. So, when I extend this edge to, so if it so happens that it is like an extended subdivided star, right. So, one star and then elongated edges of the subdivided star, then it and it so happens that everywhere it is a subdivided star, then you can easily see that it is indeed a subdivided K5, right. It is a T K5, right, because everywhere you have a subdivided star, it is like elongated edges, right. So, therefore, we can assume that one of them is such that one of the branch sets is such that it is not a subdivided star. If you follow, there are these 4 edges coming inside, and then if you start getting the connection here, and if you keep adding it here, so it will so happen that the third one will not come, and this one will not come and join here. It is, in that case it will again become a subdivided star. You can see this, right, it will look like this, it is from a common point. So, the star is subdivided, right. So, but therefore, we can assume that this will not happen. So, it will essentially go to somewhere else, maybe here, right. So, now let us take these 2 points, this point and this point, right. Now, we can see that. So, you contract this and this, when we contract, so this will become one vertex, right, one vertex, this will become one vertex. We will get a structure like this here, K4 will come here, because when we contract this thing, they will, these edges are there across, therefore K4 will come. Now what we are going to do is we will take these two as two vertices and then contract as much as required this branch, this branch, this branch and this branch. So we be considering this vertex and this and this, we can see a K33 in it, isn't it? Yeah, you can see a K33 in it, because this is on one side, say A side, this is on B side, and then this is on A side. We can put it these two on A side and these two on B side, right? So you can easily see that this is giving a K33, right? This A is connected to this B and this B. This A is connected to this B, and yeah, this is connected to this B and this. Sorry, this is. This, yeah, is connected to B, and this, of course, this is connected to B, right? This is connected to B, and this is connected to, yeah, B and B, right? So you can see a K33 in it, K33 minor in it, and we only have to bother about the minor. We don't have to explicitly show the K33 topological minor, because in the K33 minor, as we have seen already, there is a K33 topological minor. This is the next idea we needed. The last idea before the to prepare for the Kuratowsky's theorem that we need is the simple statement that if we consider a plane graph which is two connected, any two connected plane graph. So this is what we have considered, that in any two connected plane graph, every face is bounded by a cycle. This is what we want. So this is also a simple statement, because suppose we have a plane graph. Plane graph means it's drawn on the plane without the edges crossing, and it is two connected, right? If it is two connected, now we just want to show that every face has its boundary as a cycle, simple cycle. So what we do is we first consider whether this is a cycle or not. If the graph itself is a cycle, there is nothing to prove, because essentially the face has to be like this. So it has to, the cycle itself will be the boundary of the face. So we have nothing to show. So one face is outer face, one face is inner face. So otherwise, we remember there is an year decomposition. We will consider the last year, right? The added. The year decomposition means we keep adding so the years of this sort, right? So because it's a two connected graph, there is an year decomposition. Assume that it's constructed by adding years, and then consider the last year, right? Last year that is added. It can be something like this. Now this is P path. This is an H path. This is H. This is P, and this together by adding P on H, we got G final graph. Now we know that this graph G has a plane representation. It's drawn on the plane. We are only bothered about the faces of it. Now if you consider a face of G, and if it is also a face in H, we are done by induction. By induction we can say that it's a smaller graph. It's a smaller graph. We can assume that the theorem is true. So it's true. So the only case we have to bother about it is a face of G which does not contain, which is not a face of H, right? A face of G which is not a face of H. So what kind of face is that? So it's definitely is a face of G somehow which involves the path, right? Which involves the path we have removed, the year we have. So it should be finally this path. This is a path P. So it should be containing something like this. Now you see this path, right, should be contained in. So when you remove this thing, so because this area is part of some face of H, and then therefore it should be contained in some face of H like this, isn't it? So, like this, and then this is totally inside this face, right, isn't it, because it cannot cross any boundaries. So, this path, the interior region of the path has to be internal to a face in G. So, now if you add this thing, naturally this face also has to be a cycle, right. This is it's a simple idea. So, therefore, two connectivity means that any face has a boundary which is a cycle. This is the last thing we are going to meet. And now we will look at one special case of Kuratowsky's theorem, namely we will show that if the planar graph is 3 connected, then it is, if the planar graph is 3 connected, then it has a, sorry, K5 minor or K33 minor, right. So, or in other words, in other words, sorry, we are going to prove that a non-planar graph which is 3 connected, right. So, sorry, our strategy will be to prove that if a graph has K5 minor or K33 minor, then it is non-planar. First we will show that if a graph is 3 connected and without a K5 or K33 minor, then it is planar. That is what we are going to show. So, this is the statement. So, 3 connected. So, and sorry, I do not have this slide here. So, yeah, if the graph has so these are the properties. G is 3 connected and without a K5 or K33 minor, then it's planar. This is what I will prove. After that we will remove the 3 connectivity requirement and then we will argue about simply, right, 3 connectivity. So, now it is a the K5 or K33 minor free graph which is 3 connected. So, we will remember Thomason's result that in any 3 connected graph there is a edge xy, so in 3 connected graph edge xy, such that if we contract this edge xy, we will end up with a graph so where the contracted vertex xy. So, after contraction we can get a graph such that it is still 3 connected. This is what, so this is what we studied, right. So, we will use this theorem and then we will look at the edge xy which can be contracted without losing 3 connectivity. Let us say xy is the edge and then vxy is the edge which is obtained after contraction, right. So, the point is, again we are planning to use induction on the number of vertices. If you know that for all smaller graphs which are 3 connected and without K5 minor free and K33 minor free, it is planar, right. Then we will show that this graph with one more vertex also is like that. Here what we have done is to reduce the number of vertices by contracting the edge, but in the process we also retain 3 connectivity because we selected the edge to be contracted carefully, because we used the earlier result which we had proved in the as part of connectivity when we studied connectivity, that there exists an edge which can be contracted without losing 3 connectivity. So, we did not lose 3 connectivity, but reduced the number of vertices, we reduced the number of vertices. Therefore, we can say that, so the smaller graph is 3 connected. Can it have a K5 minor or a K33 minor? Of course not, because after contracting, if a K5 minor or K33 minor appeared, then already the original graph also had a K5 or K33 minor. So, by contracting it cannot produce a K5 minor or K33 minor which is not there before, right. So, therefore, the after contraction we got a smaller graph on which we can apply the induction. That means it is 3 connected and without a K5 minor or K33 minor. Thus, we can assume that there is a drawing of that graph on the plane. It can be something like this. So, the most important thing is to locate that vertex v x y, and then because we have it is a 3 connected graph. Even if you remove this vertex v x y, it will be still a 2 connected graph, because if you remove one vertex from the 3 connected graph, its connectivity still be at least 2. And then in a 2 connected graph, every phase is a cycle. So, we can see the phase of that graph. So, G say this in this, when I remove this vertex v x y in the remaining graph, which is 2 connected, the phase which contains v x y, this point v x y. So, that will be a phase, and you can see that the neighbors of v x y, which is essentially the original neighbors of x and y together, has to arrange them in such a way, right, in on this face in a circular way. Now, what we do is, we suppose we just want to call v x y as x and remove all the neighbors of y which is not neighbors of x, then some neighbors we have to delete from here, say maybe, yeah, so like that. So, some of the exclusive neighbors, only the x neighbors were present here. So, we can call it x1, x2, x3 up to xk. So, this will cut it into several regions, x1 to x2, x2 to x3, x3 to, like that, cut it into several regions, right. Now, so the question is, where are the neighbors of y? For instance, if the neighbors of y were here, all of them were in one region like this, then I could place y here and connect it here and then make connections like this here. So, that would allow me to represent G also, right. So, that will prove the theorem that this is, so G also is representable in plane. So, we will look at the complete proof in the next class, right, and complete the proof in the next class. Thank you.